Two-dimensional vectors, Level 1. In the following series of videos, we're going to cover vectors both geometrically and algebraically. In general, vectors are used to represent lines and planes in geometry, and are also used to represent quantities such as force and velocity in physics. Many quantities in geometry and physics, such as length, area, volume, temperature, mass, and time, can be described by a single real number that is scaled to an appropriate unit of measurement, like grams, which is a unit of mass. These quantities are called scalar quantities, and the real number associated with each quantity is called a scalar. Quantities such as force, displacement, velocity, and acceleration involve both a magnitude and a direction, and cannot be characterized completely by a single real number. A convenient way to represent these types of quantities is by using vectors. A vector is essentially a directed line segment, represented by an arrow. The directed line segment is constructed by an initial point P, also known as a tail, and a terminal point Q, also known as a tip or head of the vector. We can denote these vectors by writing the letters of the initial point, in this case P, and the terminal point, in this case Q, and then we draw an arrow on top of the letters as follows. Similar to a line segment from geometry, vectors have a definite measurable length. The length of a vector is referred to as the magnitude of the vector, and is denoted as follows, using the absolute value symbol, or by using double vertical bars as follows. In these videos, I will use the double vertical bars to denote the magnitude of a vector. Some textbooks will use the absolute value symbol. Unfortunately, this notation can be misleading. Many students think that they need to find the absolute value rather than the magnitude of a vector. Because of this potential confusion, I will use the double vertical bars to denote the magnitude of a vector. Next, let's talk about equivalent vectors. In general, directed line segments that have the same length, magnitude, and direction are said to be equivalent. For example, the following two vectors are equivalent because the length or magnitude of each vector is the same, and they are both pointing in the same direction. On the other hand, the following two vectors are not equivalent vectors, because one vector is longer than the second vector. In other words, the first vector has a greater magnitude compared to the second vector. Notice that both vectors are pointing in the same direction. Although they share this common characteristic, they are not considered to be equivalent vectors, because both the magnitude and direction need to be the same. Similarly, the following two vectors are also not equivalent. Notice that they have the same length, but each vector is pointing in a different direction. In this scenario, only one of the two requirements for vector equivalence is satisfied. As a final example, the following two vectors are not equivalent, since both vectors have distinct magnitudes and directions. In this case, none of the two requirements for vector equivalency is satisfied. Keep in mind that both the magnitude and direction need to be the same for two vectors to be considered equivalent. Another notation that is used to denote vectors is by assigning a lowercase boldface letter such as U, V, and W. In practice, it is pretty tricky to write boldface letters on paper. So, an alternative way to denote vectors is by using a lowercase letter with an arrow on top, similar to the way we denoted rays in geometry class. This way, we can denote vector PQ as vector V. If we wanted to denote that two vectors are equivalent or equal, all we need to do is place an equal sign between the two symbols as follows. Vector V equals vector U. Lastly, we can denote a special vector that has no specific direction. This vector is called the zero vector, and is denoted as follows. This vector has a length of 0, hence the zero vector. It is usually represented as a single point, you can think of this vector as having the same initial and terminal point. The direction of 0 vectors can technically point in any direction, but we will not bother assigning a specific direction. Let's go over a couple of examples. Name all equivalent vectors in the parallelogram shown. Alright, recall that 2 vectors are equivalent if they have the same direction and magnitude, but they don't necessarily need to be at the same location. Since we're told that this is a parallelogram, both pairs of opposite sides are congruent and parallel. Also, the diagonals of the parallelogram bisect each other. With this information at hand, we can start naming all the equivalent vectors. Recall that vectors are direction sensitive, so we need to denote the initial or tail first, followed by the head or terminal point. Vector AB is equivalent to vector DC, since both vectors have the same length. They are parallel and both point in the same direction. In the same manner, vector AD and vector BC are also equivalent, since they have the same magnitude and direction. Now, let's take a look at the diagonals. We know from elementary geometry that the diagonals of a parallelogram bisect each other. This means that vector DE and vector EB have the same magnitude or length. They also lie along the same line and point in the same direction. Notice that all requirements for vector equivalency are met. Hence, these vectors are equivalent. Finally, vector AE and vector EC are also equivalent because they have the same magnitude and direction. Again, because of the geometric properties of parallelograms. Alright, let's go over the final example. Name all the equivalent vectors in the figure shown. Quadrilateral ABCD is congruent to quadrilateral CEGF. Alright, recall that when 2 figures are congruent, corresponding angles and corresponding sides of the figure have the same measurement. This means that all of these vectors have the same length, or magnitude. Also, since right vertical angles form at point C, the corresponding sides of the quadrilaterals are also parallel to one another. With this information, we can conclude that vector BA is equivalent to vector GF. Vector CB is equivalent to vector GE. Vector DC is equivalent to vector CE. And vector AD is equivalent to vector CF. Keep in mind that both the magnitude and direction of the vectors need to be the same. Okay, in our next video, we will start learning how to describe vectors in a 2-dimensional coordinate system. 2-dimensional vectors, level 2. Alright, now that we have a better understanding of what vectors are, let's go ahead and start describing vectors more precisely with coordinate points. Recall that vectors have an initial point and a terminal point. Because vectors can be described using these 2 points, we can describe these points by using ordered pairs in a rectangular coordinate system. For example, vector v can be represented by a directed line segment that starts at the origin 0, 0 and ends at point 3, 2. Let's denote these points as P and Q, respectively. In the same manner, we can represent vector u by a directed line segment that starts at point 1, 3 and ends at point 4, 5. Let's denote these points as point R and S, respectively. Notice that we can now describe the initial and terminal point of a vector by making use of ordered pairs in a 2-dimensional coordinate system. Representing vectors in this fashion allows us to use a 2-dimensional coordinate system to precisely carry out various measurements. As an example, say that we are asked to show that vector v and vector u are equivalent. How can we use the directed line segment representation of vectors to determine if they are equivalent? Let's start with the definition of equivalent vectors. In order for 2 vectors to be equivalent, both their magnitude and direction have to be the same. Let's first check and see if the magnitude of vector v and vector u are the same. We can find the length of each vector by making use of the distance formula, learned from previous math classes. Notice that vector v is formed by point P and Q. To find the magnitude of vector v, we simply take the difference of the point's x coordinates, square the result, and add it to the difference of the y coordinates squared. And then we take the square root of this sum. Recall that this is nothing more than an application of the Pythagorean theorem. Simplifying the expression, we obtain the square root of 13 as the magnitude of vector v. In the same manner, let's calculate the length of vector u. Similar to vector v, we find the difference of the point's x coordinates, square them, and add it to the difference of the point's y coordinates squared. And then we take the square root of the sum. Simplifying the expression, we obtain the square root of 13 as the magnitude of vector u. So our first condition for vector equivalency is satisfied. Both vectors have the same magnitude. Now we need to make sure that both vectors have the same direction. Taking a look at the vectors, we see that they both have a positive slope. They seem to be pointing in the same direction. Just to make sure that this is the case, we should calculate the slope of each vector and confirm that they have the same slope. In other words, we need to check that the vectors are parallel to one another. We can determine this by calculating the rise over the run for each vector. Vector v has a rise of 2 and a run of 3. Likewise, vector u has a rise of 2 and a run of 3. Both vectors have the same slope, and both vectors are pointing in the same direction. All conditions for vector equivalency have been satisfied. So we can conclude that these two vectors are equivalent. The next concept associated with vectors that we need to understand is that a vector represents a set of directed line segments, each having the same length and direction. For example, vector v was equivalent to vector u, even though their initial and terminal points had distinct coordinate points. In the same manner, we can represent additional vectors that are equivalent to vector v. All of these vectors have the same direction and magnitude as vector v. For computational purposes, it is very convenient to work with a vector whose initial point is located at the origin. This way, the initial point is represented by the coordinate 0, 0. This representation of vector v is said to be in standard position. It is also referred to as the position vector. Notice that the standard position of a vector is essentially a directed line segment that starts at the origin and ends at a specific coordinate point of the Cartesian coordinate system. With this alternative way of representing a vector in a coordinate system, we can now describe any vector that is in standard position by simply using the coordinates of the vector's terminal point. As a final note, 0 vectors in standard position will be represented by a point located at the origin, as follows. Since both its initial and terminal points lie in the same location. In this case, both points would lie at the origin. Alright, we have seen how describing vectors by using points is pretty convenient, especially if the initial point of the vector is located at the origin. An even better way of describing a vector is by using the coordinates of its terminal point. This particular way of describing a vector is referred to as the component form of the vector. And we denote it by using angle brackets, as follows. The numbers v sub 1 and v sub 2 are called the components of the vector. Notice the similarities between the way you denote a point and the way you denote the component form of a vector in a Cartesian coordinate system. Because of this similarity, it is important to use parentheses when we are denoting points and use angle brackets when we are denoting vectors in component form. For example, vector v can be denoted as 2, 3. Here, the x component of vector v is 2, and the y component is 3. Note that the components of a vector essentially describe how much the vector leans in the direction of the x-axis and how much the vector leans in the direction of the y-axis. In the same manner, the following vectors can be denoted in component form as follows. Vector A can be written as -1, 2. vector b can be written as -2, -4, and vector c can be written as 3, -3. Keep in mind that vectors can also have a component that is equal to 0. For example, the following vectors each have a component that is equal to 0. Vector y can be written as 0, 2. Vector w can be written as -2, 0. Vector x can be written as 0, -1. And vector u can be written as 3, 0. Also note that if both the initial point and the terminal point lie in the origin, then the vector is referred to as the 0 vector, and is denoted by the following expression, 0, 0. We now have a more precise way of describing vectors, specifically by using the components of the vector. As a result, we can easily determine if two vectors are equivalent simply by making sure that their respective components are equivalent. In other words, the component form definition of a vector implies that two vectors such as v with components v sub 1 and v sub 2, and vector u with components u sub 1 and u sub 2 are equal if and only if the x components, in this case v sub 1 and u sub 1, and the y components, in this case v sub 2 and u sub 2, are equal. If we look back at the previous example, notice that both vector v and vector u had the same components. Both vectors had the same x component, in this case 3, and the same y component, in this case 2. Hence, both vectors are equivalent. The component form of a vector can also be obtained for vectors that are not in standard position. For example, vector u has an initial point given by the coordinates 1, 3, and a terminal point given by the coordinates 4, 5. We can easily find the x component of the vector by taking the x coordinate of the terminal point and subtract the x coordinate of the initial point. In this case, it will be equal to 3. In the same manner, we can take the y coordinate of the terminal point and subtract the y coordinate of the initial point. In this case, it will be equal to 2. Hence, the component form of vector u is 3, 2. In general, any directed line segment with initial point x sub 1, y sub 1, and terminal point x sub 2, y sub 2 can be represented in component form by simply finding the difference of the y coordinates for the y components and the difference of the x coordinates for the x component. Because vectors are direction sensitive, we need to make sure we subtract the coordinates of the initial points with that of the terminal point when finding the component form of the vector. Alright, in our next video, we will practice applying these new concepts and go over a couple of examples. Two-dimensional vectors, level 3. In this video, we're going to go over various examples and practice applying the concepts from the previous videos. Before we start solving problems, let's first go over one final concept associated with the magnitude of a vector. In addition to finding the component form of any directed line segments, we can also find the magnitude by simply finding the components of the vector and using the distance formula. In other words, the length, or magnitude of a vector, v, is found by taking the square root of the vector's x component squared plus the vector's y component squared, as follows. We now have two distinct ways to find the magnitude of a vector, and both involve the use of the Pythagorean theorem. If a directed line segment is represented by an initial and terminal point, we use the first formula. If the vector is represented in component form, then we use the second formula. These two formulas are very similar to each other. The only difference is the way in which the vector is described. One formula uses coordinate points, and the other uses the components of the vector. You should be comfortable using either one. In some textbooks, the magnitude or length of a vector is also referred to as the norm of the vector. Lastly, the magnitude of a vector is equal to 0 if and only if vector v is a 0 vector. Alright, let's go over a couple of examples. Find the vector from the point 1, -2 to the point 3, 7. Okay, here we are given the coordinates of point A and point B. We're asked to find the vector that starts at point A and ends at point B. In other words, we are asked to find vector AB. To find the components of this vector, we essentially need to take the coordinates of the terminal points, in this case, point B, and subtract the coordinates of the initial points, in this case, point A. We need to make sure that we subtract the terminal point from the initial point, or else we will obtain a vector that points in the opposite direction. Carrying out the subtraction, we obtain the following. Vector AB is equal to 3 minus 1 for the x component, which simplifies to 2, and 7 minus -2 for the y component, which simplifies to 9. So the vector that starts at point A and ends at point B can be represented as vector AB, with components 2, 9. Alright, let's try the next example. Find the component form and length of the vector v that has initial point 3, -7 and terminal point -2, 5. Okay, let's first plot the initial point and terminal points so we can have a visual representation of the vector. Let's label them as point A and point B respectively. Then we go ahead and draw a directed line segment from point A to point B as follows. Let's first find the component form of the vector. In order to accomplish this, we need to find the x and y components of the vector. We can find the x component of the vector by simply taking the x coordinate of the terminal points and subtract the x coordinate of the initial points. Doing that, we obtain -5 for the x component. In the same manner, we take the y coordinate of the terminal points and subtract the y coordinate of the initial points. Doing that, we obtain 12 for the y component. So the component form of vector v is represented as -5 and 12. Having found the component form of the vector, we now find the magnitude of the vector by simply taking the square of each component, adding them, and then take the square root of the result. Doing this, we obtain the final answer equal to 13. This means that the length of this vector is 13 units long. Alright, let's try the next example. Find a vector v with representation given by the directed line segment AB. Draw AB and the equivalent representation starting at the origin. Point A is -2, 2, and point B is 3, 0. Similar to the previous example, we're asked to find a vector v that is represented by the directed line segment with initial point A and terminal point B. In order to find the vector, we need to calculate the vector's components. So we go ahead and take the coordinates of B and subtract the coordinates of point A, making sure we subtract them component-wise. Doing that, we obtain the following. Vector v is equal to 3 minus -2 for the x component, which simplifies to 5, and 0 minus 2 for the y component, which simplifies to -2. So vector v has components equal to 5, -2. Now that we have the components of vector v, we go ahead and draw an equivalent vector. With initial point located at the origin, this is also referred to as a vector in standard position. Drawing the vector, we have the following. Vector v starts at the origin and terminates at point 5, -2. Notice that the terminal point of a vector in standard position has coordinates equal to the components of the vector. Okay, let's try the next problem. Find the component form of the vector v and sketch the vector with its initial point at the origin. In this problem, we are provided with the graph of a vector, along with its initial point and terminal point. We are asked to find the component of this vector. Similar to the previous examples, all we need to do is take the coordinates of the terminal point and subtract the coordinates of the vector's initial point. Doing that, we have the following. Vector v is equal to 3 minus 3 for the x component, which simplifies to 0, and negative 2 minus 4 for the y component, which simplifies to negative 6. So vector v has components equal to 0, negative 6. Now that we have the x and y components of the vector, we can go ahead and draw it in standard position. Notice that this vector has an x component of 0. This means that it only has one component, in this case, the y component. So vector v will be pointing in the negative y direction. So we start at the origin and extend the vector to the point 0, negative 6. This vector is now in standard position. Alright, let's go over the final example. Find the vectors u and v whose initial and terminal points are given. Show that u and v are equivalent and find the magnitude of the vectors. Alright, the problem is asking us to find vectors u and v. We are provided with the vector's initial and terminal points. They are essentially asking us to denote the vector in component form. Let's start with vector u. Similar to the previous examples, let's take the terminal point and subtract the initial point to obtain the components of the vector. Doing that, we obtain the following. Vector u is equivalent to 1 minus negative 4 for the x component, which simplifies to 5, and 8 minus 0 for the y component, which simplifies to 8. Alright, now we do the same for vector v and obtain the following. 7 minus 2 for the x component, which simplifies to 5, and 7 minus negative 1 for the y component, which simplifies to 8. Now that we have both vectors u and v in component form, we go ahead and compare their components to see if they are equivalent. Since the components of both vectors are identical, we conclude that they are indeed equivalent. Lastly, we go ahead and calculate the magnitude of the vectors by taking the square of each component and adding them together, making sure we take the square root of the result. Doing that, we obtain the square root of 89 as the magnitude of vector u and v. Alright, make sure you're comfortable with the component form of a vector. We will be using this form extensively throughout our studies of multivariable calculus. In our next video, we will learn various vector operations. Two-dimensional vectors, Level 4. In this video, we will learn about vector operations. This is also known as vector arithmetic. Many problems that make use of vectors require slightly more complicated calculations other than just finding the magnitude of a vector. In order to carry out these calculations, we need to learn algebraic operations with vectors. These vector operations are carried out similar to algebraic operations with real numbers. Before we start, we need to remember that a vector represents a directed line segment with a specific length known as the magnitude and a specific direction. We will be using this geometric representation of a vector to illustrate various vector operations geometrically. You can think about this vector as representing the displacement of a particle that starts at one point, the initial point, like point A, and ends at the second point, the terminal point, like point B. This type of vector is referred to as a displacement vector in physics. This vector can be denoted the same way we denoted vectors in the previous videos, by using the initial and terminal point with an arrow on top, as follows, vector AB. Or, we can also name the vector by using a single bold-faced letter with an arrow on top. Alright, let's go over the first vector operation. Our first vector operation is a scalar multiplication. This operation consists of multiplying a vector by a real number c. This operation can be denoted as c times vector v. The real number c is referred to as a scalar. Note that a scalar is not a vector, so we need to make sure we don't write an arrow on top, like we do with vectors. This way, we can distinguish a scalar from a vector. As the name suggests, Scalar multiplication of a vector can be geometrically viewed as scaling a vector by a specific factor. This can either stretch or compress the original length of a vector. It can also change the direction of a vector. For example, say you wanted to double the length of a vector. If this vector represents the displacement of a particle between 2 points, and if we wanted a particle to move twice as far in the same direction as vector v, we would denote this vector as 2 times vector v. Here, the number 2 is the scalar, and it's essentially instructing us to take vector v and double the length, making sure we keep the same direction in the process. In the same manner, if we want to reduce the length of vector v by half, we would denote it as follows: 1/2 times vector v. Here, the scalar is 1/2, and it is instructing us to take vector v and reduce its length by half, and keeping the same direction. Lastly, a vector can be multiplied by a negative scalar. Multiplication by a negative scalar forces the original vector to point in the opposite direction. This operation is denoted as negative vector v. It literally turns a vector 180 degrees in the opposite direction. In general, the scalar multiple of a vector v by a scalar c is the vector whose length is the absolute value of c times the length of vector v, and whose direction is the same as vector v. If c is greater than 0, in this case, a positive scalar, and the direction will be opposite to vector v if c is less than 0, in this case, a negative scalar. Note, if the scalar c equals 0 or vector v equals 0, then it follows that c times vector v equals 0. In the end, real numbers essentially work like scaling factors. This is why they are conveniently referred to as scalars. Now let's think about a different scenario. Say that a particle moves from point A to point B. Then, the particle changes direction and moves from point B to point C, with position vector BC. The combined effect of these movements is that the particle has moved from point A to point C. We can represent this movement by drawing a vector from point A and ending at point C, as follows. The displacement vector AC is essentially the sum of vector AB and vector BC. We can mathematically denote this sum as follows. Vector AC equals vector AB plus vector BC. In general, if we start with vectors v and u, we can geometrically find the sum of these two vectors by first moving vector u, making sure we do not change its magnitude or direction, so that its tail coincides with the head or tip of vector v, as follows. We can then define the sum, vector v plus vector u, as the vector whose initial point coincides with the initial point of vector v and extends to the terminal point of vector u. This vector is usually referred to as the resultant vector. The resultant vector is used extensively in fields such as physics and engineering, and its interpretation depends on the particular application it is being used for. In this example, the resultant vector represents the displacement of a particle from point A to point C. This method of adding vectors is sometimes called the tail-to-head method, or triangle law. This is the general procedure to add vectors geometrically. An alternative method of adding vectors is by just reversing the order in which you add both vectors. For example, say we wanted to add vector u plus vector v, as opposed to vector v plus vector u. Then we follow the same procedure. We take vector v and move it so that its tail or initial point coincides with the tip or head of vector u, and define the sum vector u plus vector v as the vector that starts from the initial point of vector u and terminates at the tip of vector v. Notice that we obtain the same resultant vector. In other words, vector v plus vector u equals vector u plus vector v. Notice that we also form a parallelogram. This illustrates yet another way of adding vectors geometrically. all we need to do is to move vector u and vector v so that they start at the same point. Then, the resultant vector lies along the diagonal of the parallelogram, with u and v as sides. This technique is referred to as the parallelogram law. Either technique can be used to find the sum of two vectors. If we wanted to add 3 or more vectors, we can essentially just apply each law multiple times. For the most part, it is a lot easier to use the triangle law when adding 3 or more vectors together. For example, if we had a third vector, say vector w, and wanted to find the sum of vector v, u, and w, we would first start with vector v and move vector u so that its tail coincides with the tip of vector v. Then, we would move vector w so that its tail coincides with the tip of vector u, as follows. Then, the resultant vector will be the vector that starts from the initial point of vector v and terminates at the tip of vector w. Again, the order in which the vectors are added does not matter. In the end, you should obtain the same resultant vector. Now let's move along to vector subtraction. Computationally, subtraction of vectors is very similar to vector addition. We can geometrically find the difference of two vectors by making use of the triangle law. Say we want to find vector v minus vector u. The easiest way to think about vector subtraction is by treating it as a vector addition problem. In other words, we want to find vector v plus negative vector u. So we take vector u and align its initial point with the tip of vector v. Normally, this is what you would do if you were adding both vectors. In the case of vector subtraction, we want to take the negative of this vector. Recall that a negative scalar flips the vector in the opposite direction. So we go ahead and change the direction of vector u as follows. Then, we can define vector v plus negative vector u as the vector whose initial point coincides with the initial point of vector v and extends to the terminal point of negative vector u. Again, similar to vector addition. We can also use the parallelogram law to find the difference. All we need to do is to make sure we change the direction of vector u so that it faces in the opposite direction. Then we align both vectors so that they start at the same initial point. The resultant vector will lie along the diagonal of the parallelogram, with negative u and v as sides. A final way to think about vector subtraction is by aligning both original vectors so that they start at the same initial point. Then we can use the fact that if we were to take vector u and add it with vector v minus vector u, we should obtain vector v. This way, we can use the triangle law to draw vector v minus vector u. In this case, the resultant vector will be drawn as follows. Personally, the first method for finding the difference between two vectors makes the most sense, but you're free to use any of these three methods when geometrically finding the difference between two vectors. Also, keep in mind that vector subtraction is just a special case of vector addition. If you were to have 3 or more vectors and are asked to carry out a combination of addition and subtraction operations with them, you treat the entire problem as if it were a vector addition problem by using the triangle law and flipping the direction of any vector with a negative sign. Alright, in our next video, we will go over various examples that make use of vector operations. Two-dimensional vectors, Level 5. In this video, we will go over various examples that make use of vector operations, specifically vector addition, vector subtraction, and scalar multiplication. We will solve these problems by using the geometric interpretation of these particular vector operations. Alright, let's go over the first example. Write each combination of vectors as a single vector. Alright, here we have line segments, connected by various vertices. Since these are line segments, we are free to assign the direction of vectors by appropriately denoting the initial and terminal points. Let's start with the first example. Here, we are asked to find the sum of vector CB and vector BA. First, let's identify each of the vectors on the diagram. Vector CB is located here, and vector BA is here. Next, we go ahead and add the vectors geometrically by applying the triangle law. Notice that the tail of vector BA is aligned with the head of vector CB. All that is left to do is to draw and determine the resultant vector. In this case, the vector will extend from the tail of vector CB towards the head of vector BA. Looking at the diagram, we see that this vector can be denoted as vector CA, and this is the resultant vector. Alright, let's try the next example. Here, we are asked to add vector AC and vector CD. Like in the previous example, let's go ahead and apply the triangle law for vectors. Notice that the tail of vector CD is aligned with the head of vector AC. This means that the resultant vector is going to have an initial point at A and a terminal point located at D. In other words, the resultant vector would be vector AD. Let's try the next problem. Here, we are asked to find the difference between vector BD and vector CD. Let's first identify vector BD and vector CD. Now, in order to carry out this difference, we can think about this problem as a special case of adding vectors. In this case, we are adding the negative of vector CD to vector BD. So, if we were to take vector CD and align its tail to the head of vector BD, we would obtain the following. Now we need to flip vector CD so that it points in the opposite direction, as follows. Now we go ahead and apply the triangle law. Notice that the resultant vector in this example would be equal to vector BC. Alright, let's try the next example. Here, we are asked to find the sum of vector AD, vector DC, and vector CB. When adding more than two vectors, the procedure is essentially the same. You want to add the vectors by using the tail to head method. You can think of this process as applying the triangle law multiple times. In the end, the resultant vector will have its initial point at A and terminal point at B. Thus, the resulting vector would be vector AB. Alright, let's move along and try a different type of problem. Given vectors u, v, and w, draw and label the resultant vector of the following vector expressions. Okay, in this problem, we are provided with three distinct vectors, each with their own magnitude and direction. The first vector expression is asking us to find and draw the resultant vector when vector u and vector v are added. We can geometrically find the sum by applying the triangle law. So we go ahead and align the tail of vector v with the head of vector u as follows. The resultant vector will then have its initial point located at the tail of vector u and its terminal point at the head of vector v. Alternatively, we can also make use of the parallelogram law and align the tails of both vectors together, and then make copies of each vector that are parallel to one another, forming the sides of the parallelogram. Using this method, we can draw the resultant vector by starting at the intersection where the tails of both vectors coincide and extending the directed line segment along the diagonal of the parallelogram. Regardless of what method you apply, you should obtain the same resultant vector. Okay, let's try the next example. Here, we are asked to find the resultant vector when we add vector v and vector w. Keep in mind that it really doesn't matter which vector you add first, as long as you follow the triangle law or parallelogram law. Everything should work out. Using the triangle law, we would obtain the following resultant vector. In the same manner, if we use the parallelogram law, we would obtain the same exact resultant vector. Alright, let's try the next example. Here, we need to find the resultant vector when we subtract vector v from vector u. The procedure for subtracting vectors is essentially the same as adding vectors. All we need to do is to make sure we flip the direction of the vector being subtracted. In this case, we first align the vectors by making use of the head-to-tail method, or triangle law. Then, we take vector v and flip it in the opposite direction. From here, the final step is to draw the resultant vector. This vector is drawn just like in the previous examples. We can also use the parallelogram law. When using this method, always make sure you flip the negative vector before applying the parallelogram law. Alright, let's move along to the next example. Here we are asked to add all three vectors. The best way to tackle these types of problems is by applying the triangle law multiple times. So we essentially need to align the head of one vector with the tail of another vector, one after the other, as follows. The resultant vector will have its initial point located in the tail of vector u, and will end at the head of vector w, as follows. Let's try the next example. Here we are asked to carry out a scalar multiplication of vector w. Recall that scalar multiplication scales a vector by changing its length, or in the case of negative scalars, it can also change the direction of a vector. In this example, we are asked to draw vector 2 times w. We can draw this expression by taking vector w and doubling the size or magnitude of the vector, as follows, keeping the same direction as the original vector. Okay, let's try the next problem. Here, we are once again asked to carry out a scalar multiplication. In this example, we are asked to scale vector u by half its size. We also have a negative sign, so we also need to change the vector's direction so that it points in the opposite direction, as follows. Alright, let's try the next example. Here we are asked to subtract two vectors. In this case, we are asked to find the difference between vector u and 3 times vector v. Similar to vector addition, we need to align the vectors by using the triangle law. In this particular example, we first need to scale vector v by a factor of 3. Then we go ahead and align the tail of vector 3v with the head of vector u. And then we flip vector 3v in the opposite direction, as follows. The resulting vector can then be drawn by connecting the initial point of vector u with the terminal point of vector 3v. Okay, let's go over the final example. Here, we are asked to carry out a scalar multiplication, a sum and difference of vectors. Let's draw the scalar multiplication of each vector. For vector u, we double the length. For vector v, we scale the vector by a third of its original length. And for vector w, we triple its original length. Next, let's go ahead and add vector 2u with vector 1/3 v by using the tail-to-tip method. Next, let's go ahead and take vector 3w and flip it in the opposite direction. Then we go ahead and align the tail of this vector with the tip of vector 1/3 v. The resultant vector would then be drawn from the tail of vector 2u to the tip of vector 3w. Alright, now that we have a better understanding of the geometry of scalar multiplication, vector addition, and vector subtraction, we are ready to learn how to carry out vector operations algebraically. In our next video, we will learn a more powerful and precise method for computing various vector operations. Two-dimensional vectors, Level 6. In the previous videos, we learned the geometric representation of vector operations, specifically vector addition, vector subtraction, and scalar multiplication. In this video, we will learn how to precisely carry out these vector operations algebraically. Let's start with scalar multiplication. Recall that we use a Cartesian coordinate plane to describe vectors. This way, we can precisely denote a vector by writing it in component form. For example, here we have vector v, along with its initial and terminal point. From the graph, we can determine the components of the vector. In this case, it would have an x component of 3 and a y component of 4. Now, let's go ahead and multiply vector v by a scalar of 2. In other words, let's double the length of the vector, while keeping the same direction. So we are essentially trying to find vector 2v. Let's first find vector 2v geometrically. Then we will check and see how scalar multiplication affects the components of the original vector v. The length of vector v is equal to 5, since we have a classical 3, 4, 5 triangle. This is one of the Pythagorean triples. So we go ahead and double the length of vector v. This vector operation doubles the magnitude of vector v, making it equal to 10. Next, let's take a look at the x component and y component of this new vector. Notice that the x component is now equal to 6, and the y component is now equal to 8. Compared to the original vector, the components of the new vector have doubled in length. In the end, multiplying vector v by a scalar of 2 changes each of the vector's components by the same scalar. In general, when multiplying a vector in component form by a scalar c, we simply multiply each component by that scalar. This is really convenient from a computational standpoint, since this allows us to precisely denote a scalar multiple of a vector algebraically. In the same manner, if we were to multiply this vector by -2, we would obtain a new vector that has a magnitude of 10, but points in the opposite direction, since -2v equals -6 for the x component and -8 for the y component. Notice that the new x and y components are now leaning towards the -x and y axis. Alright, as you just saw, computing the scalar multiplication of a vector algebraically allows us to focus on the mathematics of vectors, without dealing with the geometry of vector operations. The algebraic definition of scalar multiplication has a couple of nice applications, such as describing parallel vectors. This idea is going to be really important because many of the concepts in multivariable calculus will make use of parallel vectors. For the most part, two vectors are parallel if they have the same direction or if they point in opposite directions. Recall that the geometric representation of scalar multiplication generated new vectors that were parallel to the original vector and each other. In general, two non-zero vectors a and b are parallel if there is some scalar c such that vector a equals c times vector b. In other words, two vectors are parallel if one is a scalar multiple of the other. For example, the following vectors are parallel to one another because vector u equals 2 times vector v, vector w equals negative vector v, and vector a equals 1/2 times vector v. Furthermore, you can algebraically determine if two vectors are parallel from one another by finding a constant c such that each of the vector's components is a scalar multiple of the second vector's components. This can be done by solving for the constant c for each of the expressions that relate the vector's components. If there is a common constant c, then the vectors are parallel. On the other hand, if you don't manage to find a common constant c, then the vectors are not parallel. For example, by using the component form of vector v and the component form of vector u, we can check and see if these two vectors are parallel by equating each of the vector's components and checking if both expressions have a common scalar c. Solving each expression reveals that they indeed have a common scalar c, in this case 1/2, hence these two vectors are parallel. Let's go over two examples to illustrate scalar multiplication algebraically. Given vector v, find the following: 4 times v, -1/2 v, 0v, and -6v. Alright, to find vector 4v, we simply need to multiply each of the vector components by the scalar 4, as follows. This gives us a new vector with components equal to -8 and 12. For vector -1/2, we do the same. We multiply each of the vector's components by the scalar -1/2 and obtain 1 and -3/2 for the components of the new vector. For vector 0 times v, we simply multiply each component by 0. In this case, we obtain the 0 vector since both the x and y components are 0. Lastly, for vector -6v, we multiply each component by -6, obtaining 12 and -18 as the x and y component respectively. Alright, the algebraic representation of scalar multiplication is pretty straightforward. Make sure you multiply each component by the same scalar. Let's try the next example. Determine which of the vectors are parallel to vector z. Alright, here we are given vector z with components 3 and 2. We are asked to determine if any of these vectors are parallel to vector z. Recall that two vectors are parallel if one vector is a scalar multiple of the other vector. This means that we are essentially checking if there is a scalar k that we can multiply by vector z that yields either vector a, b, or c. Let's first check vector a. We can determine if there is a scalar k by inspection, or we can generate two equations by breaking the vectors into their components and solving for the scalar k. If we obtain exactly the same scalar for both components, then the vectors are parallel to one another. For the first vector, notice that we can actually obtain vector a by multiplying vector z by the scalar -2. Hence, vector a is parallel to vector z. Alternatively, we can also set up two equations and solve for k. So we first obtain two separate equations, one from each component. Then we go ahead and solve for k for both equations. Doing that, we obtain -2 for both components, further verifying that the vectors are parallel. For vector b, we go ahead and set up our equations and solve for the scalar k. In this case, we obtain 2/3 for the first equation, and for the second equation, we also obtain 2/3. Therefore, vector b is parallel to vector z. Lastly, let's check and see if vector c is also parallel to z. We once again set up our equations by using the parallel vector relation and solve for the scalar k. For the first equation, we obtain 1/3 for the constant, and for the second equation, we obtain -2. Since we obtain two distinct values for k, we can conclude that vector c is not parallel to vector z. We now know how to multiply a vector by a scalar algebraically. We will now learn how to add and subtract vectors algebraically. Say we have two vectors, vector v with an x component of 1 and a y component of 2, and vector u with an x component of 2 and a y component of 3. We want to find the components of the resultant vector formed by the sum of vector v and vector u. Let's first find the sum of the vectors geometrically. So we go ahead and use the triangle law to find the resultant vector. Aligning the tail of vector u with the tip of vector v, we obtain the following resultant vector. Now let's analyze the components of the resultant vector. The x component of this resultant vector is equal to 3, and the y component is equal to 5. Notice that the x component of the resultant vector is the sum of the x components of vector v and u. In the same manner, the y component of the resultant vector is equal to the sum of the y component of vector v and u. In general, the sum of vector v with components v sub 1 and v sub 2, and vector u with components u sub 1 and u sub 2 can be found simply by adding the components of each vector. In this case, the x component of the resultant vector will be equal to v sub 1 plus u sub 1, and the y component of the resultant vector will be equal to v sub 2 plus u sub 2. In the same manner, to subtract vectors, we simply subtract their components. In this case, the x component of the resultant vector would be equal to v sub 1 minus u sub 1, and the y component would be equal to v sub 2 minus u sub 2. We can also illustrate the sum of two vectors by using the parallelogram law. Once again, notice that the x components of the resultant vector is equal to the sum of the x components of vector v and u, and the y component is equal to the sum of the y components of vector v and u. Alright, in our next video, we are going to go over various examples illustrating how to use the algebraic definition of scalar multiplication and vector addition. Two-dimensional vectors, Level 7. In this video, we will go over various examples that make use of the algebraic definition of scalar multiplication and vector addition. Let's jump straight into the first example. Use vectors to determine whether the points P, Q, and R are collinear. Alright, recall that we solved a similar problem by using the segment addition postulate from geometry. This time around, we want to use vectors to show that these 3 points are collinear. One way to accomplish this is by finding the component form of two distinct vectors, with each vector having at least one common point. This way, points P, Q, and R will lie in the same line if and only if one vector is a scalar multiple of the other vector. In other words, if both vectors are parallel. Alright, let's generate two vectors. One vector will be formed by points P and Q, so we subtract the x coordinates and y coordinates to obtain the component form of vector PQ. Then, we do the same for vector PR, and subtract the x and y coordinates to obtain the component form of the vector. Notice that it really doesn't matter in which direction the vectors point. As long as both vectors have a common point, we should be able to determine that one vector is a scalar multiple of the second vector, regardless of the direction we choose. Looking at the vectors, we see by inspection that they are indeed parallel to one another, since vector PQ is 2/3 of vector PR. Hence, both vectors are parallel, and we used a common point to form the vectors, in this case, point P, which means that the points are indeed collinear. Alright, let's try the next example. Find K so that vector A and vector B are parallel. Alright, here we are given two vectors, and we are asked to find the value of K that will make both of these vectors parallel to one another. Notice that K represents the y component of vector B. We need to somehow set up a relation between both of these vectors that would be true if both vectors were indeed parallel to one another. Recall that two vectors are parallel to one another if one vector is a scalar multiple of the other vector. In other words, vector A equals C times vector B. With this relation, we can go ahead and find K. We first break apart this vector relation component-wise. This will yield two distinct equations. The x components yields the equation 3 equals C, and the y components yields the equation -2 equals C times K. We know from the first equation that C equals 3, so we go ahead and use this result and substitute this value into the second equation and solve for K. So, in order for these two vectors to be parallel, vector B has to have a y component equal to -2/3. Alright, now let's try a couple of examples that make use of vector addition. Find the sum of the given vectors and illustrate geometrically. Alright, in this example, we are given two distinct vectors, vector A with components 3 and -1, and vector B with components -2 and 4. We are asked to find the sum of these two vectors algebraically, and then we are asked to illustrate the vector operation geometrically. Recall from the previous video that the procedure to add vectors algebraically requires that we take each of the vector's x and y components and add them together to obtain the components of the resultant vector. So let's go ahead and take the x components of vector A and vector B and add them together as follows. And then we do the same for the y components of vector A and B as follows. In the end, we obtain the resultant vector in component form with an x component of 1 and a y component of 3. Now let's go ahead and use the triangle law to show that the sum of vector A and vector B actually forms a vector with an x component of 1 and a y component of 3. So we go ahead and place vector A in standard position as follows. Then we go ahead and align the tail of vector B with the head of vector A as follows. Lastly, we obtain the resultant vector by drawing a vector from the tail of vector A to the head of vector B. Notice that the resultant vector has an x component equal to 1 and a y component equal to 3. This is the same answer that we obtained by adding the vectors algebraically. Notice that adding vectors written in component form is a lot quicker and more precise. We will be carrying out various computations with vectors in multivariable calculus, and carrying out vector operations algebraically will be more convenient and will save us the trouble of consistently drawing vectors. Alright, let's try the next example. Given points O, A, and B as vertices of the parallelogram OAPB, find the coordinates of P. Here, we are provided with the coordinate points of 3 vertices of a parallelogram. We are asked to find the coordinates of point P. One way we can find the coordinates of point P is by creating 2 vectors. One vector that starts at the origin and ends at point A. Let's label this vector as vector A. The second vector starts at the origin and ends at point B. Let's label this vector as vector B. Notice that if we were to add these 2 vectors by using the parallelogram law, we would obtain a resultant vector that starts at the origin and ends at point P. We can then use the components of the resultant vector to find the coordinates of point P, since it represents the terminal point of the resultant vector. Alright, we can write vector A in component form as 1, 5, and vector B as 3, 1. Then we go ahead and add these vectors component-wise. Doing that, we obtain the resultant vector equal to 4, 6. Since the resultant vector is in standard position, the components of the vector will also match the coordinates of the terminal side. In this case, point P. This example illustrates how vectors can be used to solve many types of problems in analytical geometry by drawing vectors and using the properties of vectors to your advantage. Alright, let's go over the final example. Given vectors A and B, find the following. Okay, here we are given vectors A and B in component form. We are asked to find the magnitude of vector A, the sum of vector A and vector B, the difference of vector A and vector B, 2 times vector A, and the sum of 3 times vector A and 4 times vector B. Let's first find the magnitude of vector A. To find the magnitude of a vector in component form, we simply take the square of each of the components, add them together, and then take the square root of the result. Carrying out these operations, we obtain 5 as the magnitude of vector A. Now let's find the sum of vector A and vector B. To find the sum of vector A and vector B, we simply add them component-wise. So we add each of the vector's x components together, which results in 2, and we add each of the vector's y components together, which results in 5. The sum of vector A and vector B yields a vector with components equal to 2 and 5. Next, let's find the difference of vector A and vector B. Similar to the previous vector operation, we go ahead and find the difference by subtracting the components of each vector. In this case, we take -4 and subtract 6 for the x component. And we take 3 and subtract 2 for the y component, which results in a vector with components equal to -10 and 1. You can also think of vector subtraction as a special case of vector addition by making sure you distribute the negative sign to each of the vector's components before adding. Now let's find 2 times vector A. To calculate the scalar multiplication 2 times vector A, we simply take the scalar 2 and distribute it to both the x and y components of vector A, as follows. This results in a final vector with components equal to -8 and 6. Finally, let's find the sum of 3 times vector A and 4 times vector B. Similar to multiplication and addition of real numbers, we go ahead and follow the order of operations to find the resulting vector. We first need to carry out a scalar multiplication for vector A and B. So we go ahead and distribute the scalar to each of the vector's components. Then we go ahead and add the resulting vectors, making sure we add them component-wise. In the end, this vector operation yields a vector with components equal to 12 and 17 for the x and y components, respectively. Alright, in our next video, we will start taking a closer look at properties of vector operations. We will also learn how to prove these properties. Two-dimensional vectors, Level 8. In this video, we're going to cover properties of vector operations. It turns out that vector addition and scalar multiplication share many properties of ordinary arithmetic. The following are properties associated with vector operations. Let u, v, and w be vectors in a plane, and let c and d be scalars. Then we can express the following properties as follows. Vector u plus vector v equals vector v plus vector u. In other words, vector addition is commutative. This is known as the commutative property of vector addition. This is similar to the commutative property of addition for real numbers, which you learned way back in your Algebra 1 course. The only difference is that we are now dealing with vectors as opposed to real numbers. This property can be verified either geometrically or algebraically. For a geometric proof, we simply use the parallelogram law to illustrate this property. Notice that regardless of the order in which we add vectors v and u, we obtain the same resulting vector. Alternatively, for an algebraic proof, we essentially need to compute the left side of the vector expression and then do some basic arithmetic on the result to show that we can make the left side match the right side of the vector expression. Similar to the way you proved trigonometric identities. For this property, we simply start with the left-hand side of the expression and break the vectors into their component forms, as follows. Next, we go ahead and add the vectors component-wise. For the next step, we're going to use the commutative property of addition for real numbers and rearrange the order in which we add the vectors, since addition of real numbers is commutative. For example, 2 plus 3 yields the same answer as 3 plus 2. Notice that we are not rearranging the vectors, but rather the components of the vectors, which are real numbers. This is why we are allowed to use the commutative property of real numbers. Next, we notice that this new arrangement is nothing more than adding the components of vector v and the components of vector u. Lastly, these rearranged components represent vector v and vector u, respectively. And this completes the proof. We can denote the ending of a proof by using the letters QED, which means quod erat demonstrandum, which is Latin for that which was to be demonstrated, or which had to be proven, or what was to be demonstrated, or the very thing it was required to have shown. You can also use a tombstone mark, which is a small rectangle that means end of proof. This is a typical method you want to follow as you prove various properties throughout your multivariable calculus course. Let's take a look at our second property. The sum of vector u and vector v plus vector w is equal to vector u plus the sum of vector v and vector w. This is known as the associative property for vector addition. Again, this is similar to the associative property of addition for real numbers. We are free to add vectors in any order without affecting the resulting vector. We can geometrically prove this property by using the following diagram. Notice that the sum of vector u and vector v plus vector w yields the same resultant vector when adding vector u plus the sum of vector v and vector w. Alternatively, we can prove it algebraically as follows. We break apart each vector into its component form. Then we go ahead and add vector u and vector v component-wise. This will yield the following vector. Next, we go ahead and add these two vectors component-wise. This results in the following resultant vector. Now, the next step requires us to use the associative property of real numbers to group the real numbers in a different order, as follows. Then, it is just a matter of working backwards and rewriting the expressions until we match the target vector expression, as follows. The rest of the vector properties can be proven in a similar fashion. Many of the vector properties will depend on similar properties of real numbers to carry out the proof. Okay, let's move along to the next property. Vector u plus the zero vector is equal to vector u. This is known as the additive identity property for vectors. This property also resembles the additive identity property for real numbers. Our next property is vector u plus the negative of vector u is equal to the zero vector. This is known as the additive inverse property for vectors. Okay, notice that these four properties involve only vectors. Now let's take a look at vector properties that involve both scalars and vectors. Scalar c times scalar d times vector u is equivalent to the product of scalar c and d times vector u. Notice that the scalars are following the associative property of multiplication. In a later video, we will learn about vector multiplication. For now, keep in mind that this property only applies to scalars. I repeat, do not confuse it with vector multiplication, which is a totally different concept from scalar multiplication. The next property is the scalar quantity c plus d times vector u is equal to scalar c times vector u plus scalar d times vector u. In this property, the vector is following the distributive property of real numbers. Once again, notice that this property is applied to scalar quantities and not vectors. We will define vector multiplication in a much later video. Similar to the previous property, scalar c times the sum of vector u and v is equal to scalar c times vector u plus scalar c times vector v. This is essentially another form of the distributive property for scalars. Notice that it is the scalar that is being distributed to each of the vectors. Next, scalar 1 times vector u is equal to vector u. This is similar to the identity property of multiplication, also known as the multiplication property of 1 for real numbers. Lastly, we have scalar 0 times vector u is equal to the zero vector. This is similar to the zero product property of multiplication, which is also known as the zero product property for real numbers. Once again, these 9 properties of vectors can be verified either geometrically or algebraically. In general, any set of vectors with an accompanying set of scalars that satisfies properties 1 through 8 is a vector space. The 8 properties are referred to as the vector space axioms. In essence, the set of vectors in the plane with a set of real numbers, or scalars, forms a vector space. Vector spaces will be discussed in great detail in a first course in linear algebra, which is usually taken during or immediately after this course. Lastly, let's end the video by taking a look at one final vector property. A property that involves the length or magnitude of a vector along with a scalar is the length of a scalar multiple. The magnitude of a scalar times a vector is equal to the absolute value of the scalar times the magnitude of the vector. This can easily be proven. We start by denoting vector v in component form as follows. And then we go ahead and apply the distributive property by distributing scalar c to each of the components as follows. Next, we find the magnitude of this vector by applying the Pythagorean theorem. We essentially need to square both the x component and y component of the vector as follows. Then we go ahead and factor out the c squared term. Next, we break apart the product in the radicand. Now, it is just a matter of simplifying the expressions. Recall that the square root of a quantity squared is by definition the absolute value of that quantity, so we can rewrite this radical as the absolute value of c. Lastly, the radical expression on the right is essentially the definition of the magnitude of vector v. So we have shown that the left-hand side is equal to the right-hand side, and this ends the proof. Alright, in our next video, we will go over and cover unit vectors. Two-dimensional vectors, level 9. In this video, we will cover unit vectors, standard unit vectors, and direction of vectors. Let's first talk about unit vectors. If the magnitude of a vector happens to be equal to 1, we call the vector a unit vector. These vectors are going to be extremely useful as we cover more complicated concepts associated with multivariable calculus. In many applications involving vectors, it is very useful to find a unit vector that has the same direction as a given vector. This way, we can extract the direction of a vector and use it in various applications. If vector v is a non-zero vector in a plane, then vector u can be found by taking vector v and dividing it by the magnitude of vector v. This new vector u will have a length equal to 1, and will have the same direction as vector v, as long as vector v does not equal 0. We can denote the unit vector by using a bold lowercase u, or we can draw a hat symbol directly above letter u. This symbol lets you know that this particular vector represents a unit vector. Let's prove that the unit vector u has a length or magnitude of 1, and that it points in the same direction as vector v. Let's start with proving that the unit vector u has the same direction as the original vector v. We can show that the unit vector u has the same direction as vector v by noticing that 1 over the magnitude of vector v is essentially a positive scalar, so it will not reverse the direction of the original vector v. In addition, we are taking this scalar and multiplying it by vector v. Recall that a scalar multiple of a vector v generates vectors that are parallel to vector v, which means that vector u has the same direction as vector v. Next, let's show that the length or magnitude of vector u is equal to 1. We can show this by finding the magnitude of the unit vector u. We first replace vector u with its equivalent expression, in this case 1 over the magnitude of vector v times vector v. This is essentially the magnitude of a scalar times a vector, so we make use of the length of a scalar multiple property from the previous video and rewrite the expression as follows. The constant on the left stays positive, so we can rewrite it as follows. And finally, notice that we have the magnitude of vector v over the magnitude of vector v, which cancel out, giving us 1 as our final answer. In essence, all you need to do in order to find a unit vector is to find the magnitude of the vector and divide it to each of the components of the vector. This would generate a vector with length equal to 1, while maintaining its direction. This will be very useful later on in this course. The final things to know about unit vectors is that the unit vector u is usually called a unit vector in the direction of v. And the process of multiplying a vector v by 1 over the magnitude of v to get a unit vector is called the normalization of vector v. Alright, let's go over a numerical example. Find a unit vector in the direction of v and verify that it has a length of 1. Let's go ahead and find a unit vector in the direction of vector v. All we need to do is to find the magnitude of vector v and divide it into each of the components of vector v. The magnitude of vector v is equal to the square root of 29. Now it is just a matter of distributing the scalar 1 over the square root of 29 to each of the components as follows. The unit vector will now have an x component of -2 over the square root of 29 and y component of 5 over the square root of 29. In order to verify that this vector is indeed a unit vector, all we need to do is to find the magnitude. So we go ahead and square each of the components, add them, and then take the square root of the result. Doing this, we see that we obtain 1 as our magnitude. This shows that the unit vector u does indeed have a magnitude or length equal to 1. Now that we are familiar with unit vectors, it is time to talk about a special type of unit vectors, specifically the unit vectors with components 1, 0 and 0, 1. These unit vectors are called the standard unit vectors in a plane and are denoted as follows. On paper, we usually denote these unit vectors with a lowercase letter and draw the hat symbol on top. This is pronounced as I hat and j hat, respectively. One vector points in the direction of the x-axis, in this case, I hat, and one vector points in the direction of the y-axis, in this case, j hat. Both vectors have a length or magnitude of 1. Standard unit vectors are used to represent any vector uniquely. For example, we can represent vector v in terms of these standard unit vectors. Notice that the x component of vector v can be constructed by adding 3 I hat vectors. In the same manner, the y component of vector v can be constructed by using 5 j hat vectors. Mathematically, we can denote vector v by using standard unit vectors as follows. Vector v can be represented as the sum of the x component plus the sum of the y component, and each component can be represented as a scalar multiple of the standard unit vectors. We simplified this expression by replacing the unit vectors with I hat and j hat, respectively. This means that any vector in a plane can be expressed in terms of standard unit vectors. In this example, the expression 3 I hat and 5 j hat is called a linear combination of I and j, where the scalars 3 and 5 are the horizontal and vertical components of v, respectively. In general, any vector in a plane can be expressed by a linear combination of the standard unit vectors I and j. You can think of standard unit vectors as another way of denoting the components of a vector. Alright, now let's take a look at another way of describing vectors in a plane. Another way of expressing vectors is by describing the direction of a vector by using angles. Recall from trigonometry that a unit circle was used to define trigonometric functions. The unit circle has a radius equal to 1. We also defined an angle theta in standard position as an angle that started in the positive x-axis and rotated counterclockwise, intersecting a point xy of the unit circle. In addition, we are able to construct right triangles where the lengths of the legs represented the x-coordinate and y-coordinate of this point. By using right angle trigonometry, we are able to express the x-coordinate in terms of the angle theta as cosine of theta and the y-coordinate as sine of theta. Now let's take a look at the radius of the unit circle and convert it into a vector. This vector will be a unit vector since the length or magnitude of this radius is equal to 1. We will denote this unit vector as u hat. If u hat is a unit vector and theta is the angle measured counterclockwise from the positive x-axis to u hat, then the terminal point of u hat lies on the unit circle. The components of this unit vector will equal to cosine of theta I hat plus sine of theta j hat. This is another way of denoting a unit vector whose direction is expressed in terms of an angle. We can extend this definition to any non-zero vector v that makes an angle theta with a positive x-axis. The direction, in this case, will be the same as a unit vector. The only difference is that the vector will be scaled by the magnitude of vector v. We can denote vector v as follows. Vector v equals the magnitude of vector v times cosine of theta I hat plus the magnitude of v times sine of theta j hat. For example, say I have vector v with a magnitude of 3, and it also makes an angle of 30 degrees, or pi over 6 radians, with a positive x-axis. To write vector v as a linear combination of the standard unit vectors I hat and j hat, we simply take the magnitude of vector v, in this case 3, and multiply it by cosine of pi over 6 to obtain the horizontal or I hat direction, and multiply 3 by sine of pi over 6 to obtain the vertical or j hat direction. Simplifying the expression, we obtain the following. 3 times the square root of 3 over 2 I hat plus 3 over 2 j hat. When evaluating trigonometric functions, make sure your calculator is in the correct mode, either degrees or radians. Alright, in our next video, we will go over various examples that make use of unit vectors. Two-dimensional vectors, level 10. In this video, we're going to go over various examples involving unit vectors. Let's jump straight into the first example. Given vectors a and b, find the following. Okay, here we're given vectors a and b, written in terms of the standard unit vectors I and j. Recall that we can use this and the component form of a vector interchangeably. With this in mind, let's find the magnitude of vector a. So we go ahead and square each of the vector's components, in this case, I hat and j hat. Add the result and take the square root of the result, which simplifies to the square root of 13. Alright, now let's find 3 times vector a plus 4 times vector b. We first need to carry out a scalar multiplication for each vector as follows, making sure we distribute the scalar for each unit vector. Then we collect like unit vectors, which simplifies to 10 I hat plus 11 j hat. Alright, let's try the next example. Find a unit vector that has the direction opposite to vector v. Okay, similar to the previous problem, let's first find the unit vector by finding the magnitude of vector v. Using the Pythagorean theorem, we obtain 13 for the magnitude. Next, let's go ahead and normalize vector v by dividing each component by 13 as follows. This yields a unit vector equal to 12 over 13 I hat minus 5 over 13 j hat. Next, we want to find a vector that points in the opposite direction to this vector. The easiest way to find this vector is by multiplying the components of our unit vector by the scalar -1. Doing that, we obtain the following expression for our unit vector, -12 over 13 plus 5 over 13. Notice that unit vectors are useful in extracting the direction of a vector. Once you have the components for the direction of a unit vector, you're able to scale this unit vector to any length, and it will be parallel to the original vector. Let's try the next example. Find vector v with magnitude equal to 2 and the same direction as vector w, and then find the angle that vector v makes with a positive x-axis. Alright, we first need to find a unit vector that has the same direction as vector w. Once we have those components, we can easily scale the unit vector to obtain vector v. So we first need to find the magnitude of vector w. Using the Pythagorean theorem and simplifying, we obtain 2 root 3. Now we divide each of the components of vector w by this magnitude as follows. Next, we go ahead and take this unit vector and scale it by a factor of 2 to obtain vector v, which will have the same direction as vector w, but will have a magnitude equal to 2. Simplifying the expressions, we obtain 1 and the square root of 3 for the x and y components, respectively. Now we need to find the angle that this vector makes with the x-axis. We can easily find this by using the components of the vector to form a right triangle, and then use trigonometry to find the angle. In this case, we solve for theta by computing tangent inverse of the square root of 3, which equals 60 degrees, or pi over 3 radians. Alright, let's go over the next example. Find the component form of vector v plus vector w given the magnitudes of vectors v and w and the angle that vector v and w make with a positive x-axis. Alright, here we need to find the component form of the resultant vector created by adding vectors v and w. We're given the magnitude and the direction of each vector in terms of theta, which is the angle that the vectors make with the positive x-axis. This means that we can denote the components of each vector by using the alternative form of a unit vector that makes use of trigonometric expressions. This is nothing more than using right triangle trigonometry to find the x and y components of the vector. So let's first find the components of vector v. Since this vector has a direction of 0 degrees relative to the positive x-axis, it will only have one component, in this case, I hat, since cosine of 0 equals 1, and sine of 0 equals 0. Then we go ahead and multiply the unit vector by the magnitude of vector v, obtaining the components 3 and 0. Next, let's do the same for vector w. Let's first find I hat and j hat by using right triangle trigonometry. In this case, I hat will be equal to cosine of 120 degrees, and j hat will be equal to sine of 120 degrees, which simplifies to the following expression. Then, we go ahead and multiply each component by the magnitude of vector w as follows. In the end, we obtain negative 5 over 2 and 5 square root 3 over 2 for the components of vector w. Lastly, we simply add the vectors component-wise as follows, obtaining the resulting vector 1/2 and 5 square root 3 over 2. Notice that using angles to describe the direction is essentially an application of right triangle trigonometry. We will be making use of angles to denote the direction of vectors in various applications throughout our multivariable calculus course. Alright, let's go over the next example. Find scalars a and b such that vector v equals a times vector u plus b times vector w. The easiest way to figure out the scalars is by setting up a vector equation and separate it component-wise, and then solve the system of equations for both scalars a and b. So let's go ahead and substitute the component forms of vector v, u, and w into the given vector equation. Next, let's rewrite each vector in terms of the standard unit vectors I and j. Next, let's go ahead and distribute scalars a and b. Then, let's add all the terms containing the unit vector I and add all the terms containing the unit vector j. By doing this, and factoring out each of the unit vectors, we can clearly see that in order for this vector equation to be true, we need the I hat scalars and j hat scalars to be equal to each other. In other words, the equations 3 equals a plus b and the equation 3 equals 2a minus b must also be true. So we go ahead and solve this system of equations by adding the equations together and solving for a, and then use this value to solve for b. In the end, we need a to be equal to 2 and b to be equal to 1. Alright, let's end the video by going over the final example. Find unit vectors parallel to and perpendicular to the graph f of x equals negative x squared plus 5 at the point 1, 4. Alright, let's sketch the graph of f of x and the point to get a visual of this problem. We need to find vectors that are both parallel and perpendicular to this function at this particular point. In order to find a unit vector, we first need to determine the direction or components of a vector that is either parallel or perpendicular to this function at the given point, and then normalize the vector. We can easily find the direction of these vectors by using the slope of the tangent line at this point. We can figure this out by taking the derivative of the function and evaluating it at x equals 1. Doing that, we obtain negative 2 for the slope. This means that one possible vector that lies and has the same direction as this slope will be the vector with components 1 and negative 2. Let's call this vector v. So now we need to find the magnitude of this vector, which ends up being equal to root 5. Now we can find the unit vector. Notice that there are two distinct unit vectors that are parallel to the graph at this point. We can denote these two unit vectors by multiplying the components of vector v by positive or negative 1 over the square root of 5. Alright, to find the vectors that are perpendicular to this graph at this point, we essentially take the negative reciprocal of the slope of the tangent line, which in this case is 1/2. Then we find a vector, let's call it vector w, that has components along this slope. One possible vector would have components equal to 2 and 1. Now, let's normalize this vector so we find the magnitude of this vector, which is equal to the square root of 5. And then we divide each of the vector's components by this scalar. Once again, notice that there are two unit vectors that are perpendicular to this function at the given point. So we need to multiply the components by positive and negative 1 over the square root of 5. Alright, in our next video, we will go over some common applications that make use of vectors. Two-dimensional vectors, Level 11. In this video, we will go over a couple of applications that make use of vectors. For the most part, vectors are useful in many aspects of physics and engineering, especially when dealing with forces. A force can be represented by a vector because it has both a magnitude, measured in pound force, or newtons, and a direction. If several forces are acting on an object, the resultant force experienced by the object is the vector sum of these forces. For example, say we had a box in the ground, and someone decides to push the box to the right. The resultant force would just be this force, since it is the only force that is acting horizontally on the box. If, on the other hand, a second person decides to push the box to the left, we would now have two distinct forces acting on the box. Notice that both forces are horizontal. This means that both forces only have one component, in this case the horizontal or I hat component. The resultant force can easily be found by geometrically or algebraically adding all the forces. If the person on the left pushes with a greater magnitude, the resulting vector will point towards the positive x-axis, and the box will start moving in that direction as well. On the other hand, if the person on the right pushes with a greater magnitude, then the resulting vector will point towards the negative x-axis, and the box will start moving to the left. Let's go over 3 examples to illustrate how to solve resultant force problems. Alex pulls a wagon along the sidewalk with a force of 60 newtons, exerted at an angle of 42 degrees above the horizontal. Find the horizontal and vertical components of the force. Alright, when dealing with applications of vectors that involve forces, it is extremely important to find the component form of every single force acting on the body. This way you can easily find the resultant force. by adding all the forces component-wise. In this example, Alex is pulling on a wagon with a force of 60 newtons at an angle of 42 degrees above the horizontal. We can easily find the components of this force by using right triangle trigonometry. In this case, the x or I hat component will be equal to 60 times cosine of 42, and the y or j hat component will be equal to 60 times sine of 42. Approximating the expressions, we obtain 44.6 newtons for the x component and 40.1 newtons for the y component, which represent the I hat horizontal and j hat vertical components, respectively. For the most part, finding the components of the force is the first step in solving resulting vector problems. Alright, let's try the next example. Two tugboats tow an ocean liner. Each boat is pulling with a force of 400 pounds at an angle of 20 degrees and negative 20 degrees from the horizontal, respectively. What is the resultant force on the ocean liner? Alright, here we want to find the resultant force on the ocean liner due to the combined pull of two tugboats. Recall that finding the resultant force requires that we add all the forces acting on a body. We accomplish this by adding the forces component-wise. So let's go ahead and first find the components of each force, and then we will add them together to find the resultant force. Similar to the previous example, we easily find the components by using right triangle trigonometry. The components for the first force are going to be equal to 400 cosine of 20 degrees for the x component and 400 times sine of 20 degrees for the y component. Approximating the components, we obtain 375.9 pounds and 136.8 pounds for the x and y components, respectively. For the second force, the component's magnitude will be the same as the first force, but one component will have a different direction. In this case, the y or j hat component will be pointing in the negative direction relative to the Cartesian coordinate system. You can mentally include any negative signs in your components as long as the diagram justifies that assignment. You can also use the standard conventions for measuring angles and use negative 20 degrees as your angle. This will assign the correct direction for you automatically. Personally, I like to include the negative direction by analyzing the vectors on the drawing, as opposed to using the standard conventions for measuring angles. Alright, approximating the components, we obtain 375.9 pounds and negative 136.8 pounds for the x and y components, respectively. The final step is to add both of these forces component-wise. Doing that, we obtain the resulting vector equal to 751.8 pounds and 0 pounds for the x and y components, respectively. Notice that the y components cancel out because they were equal in magnitude and opposite in direction, and the x components of both forces were added together. In the end, the ocean liner is being pulled with a force of about 752 pounds in the direction of the positive x-axis. Now let's try the final example that contains three forces. Three forces with magnitudes of 400 newtons, 280 newtons, and 350 newtons act on an object at angles of negative 30 degrees, 45 degrees, and 135 degrees, respectively, with a positive x-axis. Find the direction and magnitude of the resultant force. Alright, let's first draw a diagram to help us solve this problem. Let's use a Cartesian coordinate system to draw and label the forces. For this problem, we will use the origin to represent the center of the object for which all three forces are acting on. The 400 Newton force will be located at 30 degrees below the x-axis. The 280 Newton force will be located at 45 degrees above the x-axis, and the 350 Newton force will be located at 135 degrees from the positive x-axis. Similar to the previous example, we need to find the components of all three forces and then add them together to find the resultant force. the 400 Newton force will have 200 times the square root of 3 and negative 200 for the x and y components, respectively. Notice that we can use special triangles to find an exact expression for the components of the forces. Next, we find the components of the second force, which equals 140 times the square root of 2 for both the x and y components. For the final force, we can either use the angle provided to us, in this case 135 degrees, or use the smaller angle that it makes with the negative x-axis, in this case 45 degrees. We just need to make sure that we label each of the components' direction correctly. Doing that, we obtain negative 175 times the square root of 2 and 175 times the square root of 2 for the x and y components, respectively. Now it is just a matter of adding these forces component-wise. Doing that, we obtain 200 times the square root of 3 minus 35 times the square root of 2 for the x component and negative 200 plus 315 times the square root of 2 for the y component. Computing and approximating the magnitude of the resultant force, we obtain 385.2 newtons. The final step is to find the direction of the resultant force. We can easily do this by using inverse tangent along with the components of the resultant force. We approximate the direction to be equal to 39.6 degrees, measured from the positive x-axis. Alright, in our next video, we will go over static equilibrium problems. Two-dimensional vectors, level 12. In this video, we will go over how to solve static equilibrium problems. In general, when an object is stationary or at rest, we say it is in a state of static equilibrium. When an object is in this state, the sum of the forces acting on the object must be equal to 0. For example, say we had an object sitting on a table. In its current position, the trophy is not moving, but if the table is suddenly and rapidly removed, the trophy will fall to the ground and break. What force caused the trophy to fall down immediately after removing the table? The force responsible is the force of gravity. This force is perhaps the most intuitive force in our lives, since it pulls us towards the center of the earth on a daily basis. The magnitude of this force is our weight, which is the product of our mass and the gravitational acceleration. The direction of this force is always towards the center of the earth. Let's go ahead and place the trophy back on the table. Since the trophy has a mass, it will experience a gravitational force equal to its mass m times the gravitational acceleration g, pushing it down towards the center of the earth. Once again, this is nothing more than the object's weight. Now, the reason why the trophy does not break the table and move towards the center of the earth is because the table is pushing the trophy in the opposite direction, and the magnitude of this force just happens to be the same as the force of gravity exerted on the trophy. Hence, the resultant force is equal to 0, and the trophy remains motionless. When an object is in a state of static equilibrium, the sum of the forces acting on the object must be equal to 0. In other words, the resultant force equals 0. These types of problems are solved more extensively and in greater detail in a typical physics course. For this multivariable calculus course, we will go over 3 basic examples. Naveen weighs 42 pounds. He is sitting on a swing when his sister, Vianney, pulls him and the swing back horizontally through an angle of 30 degrees and then stops. Find the tension in the ropes of the swing and the magnitude of the force exerted by Vianney. Alright, the figure of this situation is shown below. Notice that Naveen is motionless at the moment that Vianney stops swinging back. At this point, Vianney is pulling with enough force to keep Naveen in a state of static equilibrium. In addition to Vianney's force, Naveen is under the influence of 2 other forces, the gravitational force and the tension force on the ropes. We are asked to find the magnitude of this tension force, and the magnitude of the force exerted by VNA. Similar to the way we solve resultant force problems, we need to find the component form of all the forces exerted on the object. Then we go ahead and add them component-wise. And finally, we take this sum and set it equal to the 0 vector. Alright, let's go ahead and first find the component form of all the forces acting on Naveen. Using the geometry of the diagram, we can draw a right triangle with the ropes representing the hypotenuse and the x and y components of the tension force representing the legs. For this problem, you are free to use the 30-degree angle or the 60-degree angle that is formed by the sides of the right triangle, as long as you apply the trigonometric ratios correctly and assign the correct direction to the x and y components, everything will work out. I'm going to use the 60-degree angle and use it to find the components of the tension force. In this case, the x component of the tension force will be equal to the magnitude of the tension force, which is currently not known, times cosine of 60 degrees, and the y component will be equal to the magnitude of the tension force times sine of 60 degrees. Alright, now let's find the components of the gravitational force acting on Naveen. Since the gravitational force is always pointing towards the center of the Earth, it will only have one component. In this case, the vertical or y component and its magnitude will be equal to Naveen's weight. Also notice that it will be negative since it is pointing in the direction of the negative y-axis. So the components of the gravitational force are going to be equal to 0 for the x component and negative 42 pounds for the y component. Now let's find an expression for the components of VNA's force. Similar to the gravitational force, this force will only have one component, which is facing towards the positive x-axis. So the component form of VNA's force will be equal to the magnitude of VNA's pulling force, which is currently not known, for the x component, and 0 for the y component. Now that we have all three forces, we go ahead and add the forces component-wise. Also, since this is a static equilibrium problem, we also need to set it equal to the 0 vector, as follows. This expression allows us to generate two separate equations, one for the x component and one for the y component. In essence, we are dealing with a system of equations. In this case, we have two unknowns, which require two equations to solve, and we just happen to have those equations. So now, let's go ahead and solve for the tension force with the second equation. Approximating the expression, we obtain about 48.5 pounds for the tension force. Lastly, we use this value in the first equation to solve and approximate VNA's force, which is approximately equal to 24.3 pounds. Alright, let's try the next example. The tension at each end of the chain has a magnitude of 25 newtons. What is the weight of the chain? Assume that the weight of the chain is concentrated at the midpoint of the chain. Alright, here we have a hanging chain under tension, forming an angle of 37 degrees with the horizontal portion of the edges. We are also advised to assume that the weight of the chain is located at the midpoint of the chain. This means that we are going to have three distinct forces acting on the chain focused at the midpoint. Similar to the previous example, let's first find an expression for the components of all three forces. For the first tension force, the x component will be equal to the magnitude of the tension force, in this case 25 newtons, times cosine of 37 degrees, and this component will be negative since it is pointing in the direction of the negative x-axis. The y component, on the other hand, will be equal to 25 newtons times sine of 37 degrees, and it will be pointing towards the positive y-axis. For the second tension force, the magnitudes of both components will be the same, but the x component will be pointing towards the positive x-axis. Lastly, the gravitational force will be pointing directly down towards the center of the Earth, so its components will be equal to 0 for the x component and negative times the magnitude of the weight, which is currently unknown. Next, we go ahead and add these 3 vectors and set them equal to the 0 vector. Now we are able to generate our 2 equations by adding the x components together and the y components together. Doing that, we obtain the following equations. Notice that the first equation represents the sum of all the x components acting on the chain, and it is composed of only 2 forces, in this case, the x component of each of the tension force. Since this problem is highly symmetrical, we expect these 2 forces to cancel out, and this equation confirms that observation. The second equation tells us that the entire weight of the chain is being held by the vertical components of the tension forces. So we go ahead and solve for the weight. Doing that, in approximating the expression, we obtain 30.1 newtons for the weight of the chain. Alright, let's go over the final example. Use the figure below to determine the tension in each cable supporting the given load. Similar to the previous examples, let's start by finding the components of each force. The first tension force will have the following components, and the second tension force components will be equal to the following. Finally, the gravitational force will have the following values for its components. Notice that both tension forces are unknowns. Since this problem lacks symmetry, we need to get a little bit more involved in order to find the values of these forces. Let's go ahead and add these forces and set the expressions equal to the 0 vector. From here, let's extract our 2 equations, one from each component, as follows. Now we are face to face with a system of equations with 2 unknowns. At this point, it is just a matter of solving for one of the unknown tensions from one equation and substituting it back into the second equation and solving for the unknown variables. So solving for the first tension force, we obtain the following. Then we go ahead and substitute this expression into the first equation as follows. We proceed by solving for the magnitude of the second force, which is approximately equal to 1,958.1 pounds. From here, we use this value and solve for the second tension force, which is approximately equal to 2,638.2 pounds. Alright, in our next video, we will go over distance and bearing problems. 2-dimensional vectors, level 13. In this video, we will go over how to solve distance and bearing problems. In the fields of surveying and navigation, the bearing of a line L is the acute angle formed by a fixed north-south line and the line L. The notation used to designate the bearing of a line begins with N or S for north or south, followed by the number of degrees in the angle, and ends with E or W for east or west. All bearings are measured in a horizontal plane. For example, the following bearings will be denoted as follows. The bearing of point B from A will be pronounced as 40 degrees east of north. Notice that we start on the line that faces north and then move 40 degrees towards the east. The second bearing would be denoted as follows, and would be pronounced as 65 degrees west of north. Once again, notice that we start on the line facing north and move towards the west, 65 degrees, and stop. The third bearing will be denoted as follows, and it would be pronounced as 70 degrees east of south. And finally, the last bearing will be denoted as follows, and it will be pronounced as 20 degrees west of south. If you're dealing with a problem that involves air navigation, the bearing of an airplane will usually be measured in degrees and clockwise from north. This could be confusing because it goes in the opposite direction of the standard angle convention learned in your math courses. For example, if these same bearings represented the direction of an airplane, they would be denoted as follows. The first vector would have a bearing of 40 degrees. The second vector would have a bearing of 295 degrees. And the third vector would have a bearing of 110 degrees. And the last vector would have a bearing of 200 degrees. Alright, let's go over a couple of examples. A boat travels 72 miles on a course of bearing 27 degrees east of north, and then changes its course to travel 37 miles at 55 degrees east of north. How far north and how far east has the boat traveled on this 109-mile trip? Alright, we can go ahead and solve this problem by using vectors to represent each of the two bearings, with the magnitude of each vector representing the distance traveled. We can figure out how far north and how far east the boat traveled by finding the resulting vector and using its components to determine how far the boat traveled. Alright, for the first 72-mile trip, we go ahead and start at the origin and draw a vector that starts north and moves towards the east at an angle of 27 degrees as follows. This bearing represents the first 72-mile trip. Let's denote this vector as vector v. Now, for the next trip, we need to draw the cardinal directions on the tip of vector v and use it to draw the next bearing. In this case, we once again start at the direction facing north and move 55 degrees towards the east as follows. Let's label this vector as vector u. Now that we have both vectors, we can go ahead and find the components of each vector, and then add the vectors component-wise in order to find the components of the resulting vector. Looking at the diagram, we see that we can use either the 27-degree angle or 63-degree angle to find the components of vector v. And we can use either 55 degrees or 35 degrees to find the components of vector u. It really does not matter which angle you use as long as you apply the trigonometric ratios correctly. Using 63 degrees for vector v, we obtain the following expression for the components. And using 35 degrees for vector u, we obtain the following for the components. Now it is just a matter of finding the resulting vector by adding vector v and u component-wise. Doing that, we obtain 63 miles for the x component and 85 miles for the y component. So the boat traveled 63 miles towards the east and 85 miles towards the north. Alright, let's go over the next example. A person is riding in a hot air balloon. For the first hour and a half, the wind current is a constant 22 miles per hour in the direction 37.5 degrees east of north. Then, the wind current changes to 18.5 miles per hour and heads the balloon in the direction 52.5 degrees east of south. If this continues for another 2 hours, how far is the balloon from its starting point? What is the bearing of the balloon from its starting point? Similar to the previous problem, let's first draw a diagram to get a visual of the movements of this air balloon. Let's start with the first bearing. We know that this bearing will be 37.5 degrees east from north. Now we need to figure out the distance that this balloon travels in this particular direction. We know from the problem that the balloon will travel at 22 miles per hour for an hour and a half. We can easily find the distance traveled by using the classical distance equals rate times time formula. Computing the distance for this first trip, we obtain 33 miles. Let's go ahead and label this vector as vector v. Then, the balloon changes direction and will now move at a bearing of 52.5 degrees east of south. So we draw the cardinal directions on the head of the first vector. From here, we start south and move towards the east at an angle of 52.5 degrees. Next, we need to find the distance traveled on this second trip. This time around, the balloon is moving at 18.5 miles per hour for 2 hours. Once again, we make use of the formula, obtaining 37 miles. Let's call this vector vector u. At this point, it is just a matter of adding both vectors v and u component-wise. Let's first find the components of each vector. Using the 37.5 degree angle, we obtain the following expression for the components of vector v. And using the 52.5 degree angle, we obtain the following expression for the components of vector u. Notice that the y component is negative, since it is pointing towards the negative y-axis. Next, we go ahead and add vector v and vector u component-wise. Doing that, we obtain the following. Finally, we go ahead and find the magnitude of the resulting vector, which is approximately equal to 49.6 miles. We can easily find the direction by using the components of the resulting vector by using inverse tangent. Doing that, we obtain 4.23 degrees. This angle represents the angle that the vector makes with the positive x-axis. We need to take 90 degrees and subtract this angle to obtain the requested bearing. Doing that, we obtain 85.8 degrees east from north. Alright, let's go over the final example. An airplane is traveling at a fixed altitude with a negligible wind factor. The airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees. As the airplane reaches a certain point, it encounters wind with a velocity of 70 miles per hour in the direction 45 degrees east of north. What are the resulting speed, ground speed, and direction of the airplane? Alright, in this problem, the path and speed of an airplane is being altered due to wind. This is similar to the way in which a boat's path and speed can be altered by water current. Because of this wind, we need to find the true course or track of the plane. This is nothing more than the direction of the resulting velocity of the plane and wind. We also want to find the ground speed of the plane. This would be equal to the magnitude of the resulting velocity. Note that speed refers to the magnitude of the velocity vector. In physics, these two quantities are different but related to each other, with speed being a scalar and velocity being a vector. Okay, like always, let's start by drawing a diagram. Since this is an air navigation problem, the bearing will be measured from the north clockwise. So a bearing of 330 degrees will be represented as follows. This is also equivalent to 120 degrees measured from the positive x-axis. Next, we go ahead and draw the vector representing the wind velocity. In this case, it will point 45 degrees east of north. Now it is just a matter of finding the components of each velocity. For the components of the velocity of the plane, I will use the 120 degree angle. This will take care of the negative and positive signs on the components automatically. Finding an expression for the components, we obtain the following. And doing the same for the wind velocity, we obtain the following. Next, we go ahead and add the vectors component-wise. Doing that, we obtain the following for the resulting velocity. The final step is to find the magnitude and direction. In this case, the magnitude will be approximately equal to 522.5 miles per hour, and the direction will be equal to 67.4 degrees after using inverse tangent. But we need to adjust this angle. Adjusting the angle and using the standard conventions used in air navigation, we obtain 337.4 degrees. So the new speed of the airplane will be 522.5 miles per hour at a bearing of 337.4 degrees. Alright, and this ends the two-dimensional vector series. In our next series of videos, we will go over three-dimensional vectors.